Hello, everyone. I'm Walter Brennan from EXP, and welcome back to the TEA's Theme Park Design Series. Before we get started, a couple of housekeeping items. Number one, this event is being recorded, so you have been warned. As we go, if you have any questions in the presentation, please put them into the chat, and we will address those in the Q&A session at the very end. So feel free to ask any questions. So the purpose of this series is to shine a spotlight on some of the many disciplines it takes to put together some themed entertainment attractions. The intent is to give students and veteran TEA members alike an opportunity to learn more about a very specific discipline that they may not know anything about or know very little. To pull the curtain back a little bit, if you will, and see some of the magic behind the scenes. Go ahead to the next slide, Mike. This is the third of a series of events that will focus on specific disciplines like the ones you see here. In the first session, we dove into the world of landscape architecture, learning that it's the first impression that guests get as they approach a new attraction, and it's also the first chance to start to tell the story of that experience. In the second session, we learned that architecture is essentially the heart of a facility design, and why the architect is considered the master builder. From life safety to accessibility to queue design, the architect has a lot of unique challenges when it comes to theme park facility to design. For those two previous sessions, those have been recorded and are available on the TEA's YouTube channel. With that, I'd like to hand it over to my friends Mike Waggoner and George Sun from Pickney, Waggoner and Castle to introduce themselves and tell us all about structural engineering in the themed entertainment industry. Take it away, Mike.
Thank you, Walter. I'm Mike Waggoner, principal at Pickney, Waggoner and Castle. A little bit about our history. I started in theme park design in 1989. We did E.T.'s Adventure out at Universal Studios. It was a lift from something that was already completed in Florida, and so our job was just to Californicate the drawings and create a building that wouldn't fall over in an earthquake. The reason I got the job, I was probably one of the younger engineers in the office, and nobody wanted to fly to Florida. It was in the middle of winter. All the flights at that time went through Chicago. Nobody wanted to do that. So I got elected to take on the project, and it's been fantastic because I met a lot of people in the industry, and I met a lot of friends that are still friends today. And then go ahead, George.
Afternoon, my name is George Sun. I'm also a principal at FWC, and I have about 27 years of experience in theme park elements and Rockwood design, as well as the general structural engineering. I like the theme elements work in the Rockwood design. It's interesting and challenging at the same time than your traditional buildings. It's interesting to see how concept turns into reality and how there's a story behind each of the design.
Great. So Walter kind of already did the intro. Obviously, we're doing structural engineering. In our run through earlier with Walter, he told me that I need to explain some engineering concepts to you. So we'll be going over a few engineering concepts. There won't be a test at the end, so don't be afraid of that. We're going to talk about facility buildings. The SEOR, Structural Engineer of Record, is responsible for facility buildings. Most of the time, themed elements are done by vendors or specialty contractors that hire their own structural engineers to do that work. Ride foundations typically are done by the structural engineer of record, but the ride structure itself and the ride systems are done by a ride vendor who has their own engineers as well. We generally start in the process with a creative design and initial blue sky documents where we're just looking at sketches and renderings and very loosely configured drawings that we start with. From there, we go to structural systems and support layouts. We try to capture the unique configurations in some of the themed buildings. And we look at any sort of special loading and environment issues that might take place during the design and life of the building. So oftentimes the first drawings we're looking at look something like this. Certainly for us to price our work, it looks something like this. And then we start to get a sense of how we're going to structure some of these things in conjunction with the architects to try to figure out how we can make all of this chaos come into some sort of sense of structure. The types of facilities that we're going to talk about today from a facility design standpoint, we'll go over a black box ride, which is a ride that's housed in a large space, typically. Oftentimes, today we're using Butler buildings, and back when I did ET's Adventure, it was a tilt-up building in Florida. So large open buildings with high ceilings so that you can put an entire attraction inside. We're going to look also at theme structures, and they're designed to be integral with the guest experience with geometries, which will help create a sense of wonder and become part of the story that's being told. So the geometries and the configurations are much more complicated. We're also going to look at restaurant and retail spaces, which are highly functional and generally pretty simple structural geometries, but highly themed, particularly on the exterior and in the public spaces through ornate facade treatments and ceiling configurations. So loading and performance. Oftentimes, structures will have dynamic loading from ride or animatronics. Certainly, some of the projects I've done, the animatronic loading is actually higher than some of the ride loads. We also need to look at environmental loading, wind, seismic, and temperature change. And something that's, I think, unique to, or largely unique to theme park design is there's a separate code for property insurance called FM Global, which often dictates our design criteria that we're going to apply to the building, which is in excess of the building code, trying to limit property damage, because the building code really isn't structured around limiting property damage, it's structured around life safety. We have to consider occupancy. The higher the occupancy, the higher the risk category of the building, which increases our design standards. We're always looking at the mechanical, electrical, and plumbing, particularly the mechanical, electrical below grade is, we have lots of stories about large banks of conduits going under footings that we can tell. And then the mechanical inside the building, trying to weave all of the ductwork in these big spaces that require a lot of heating and cooling. We need to get that ductwork through the structure without having clash. We have to look at exposure and corrosion. A lot of times we'll find that the particular attraction or ride has a water component to it or a fog component to it, and corrosion and exposure to that is a big consideration as well. Also, we're often dealing with big spaces, so we're dealing with long spans. Deflection and vibration are very important to consider in terms of the guest experience and how things that even hanging things from a long span truss, roof truss, vibration can impact how the screens are supported on the interior of a dark ride, where the screen vibrates, not a good thing. So paying attention to all of those things is very important. And finally, ride loads and themed elements. Those are a lot of vendor input. Oftentimes, we don't have exact numbers for those because the vendors typically come on later than what we start our process. And so we have to make certain assumptions and then validate those assumptions as we continue with the design. So that's what we're going to cover on facility design. And I'm going to turn that over to George, and he's going to talk about some themed elements.
So I will be talking about theme elements, and the theme elements can be categorized into two different types. There's rock work and show set elements. Now, why these are important? Because the weight of these theme elements are important to the facility structures. And for rock work, you could generalize as anything that is carved or sculpted on site. So there are like carved plaster. These are like your plaster that you use for home. It weighs, depending on the thickness, it weighs roughly about 10 to 30 pounds per square foot. And then there's shotcrete, which is lightweight concrete, and that weighs about 25 to 50 pounds per square foot. And also there are some lightweight material, specialty products such as polygym. These are specialty epoxy product that can be placed and carved and sculpted. And they're usually very light, somewhere between 3 to 10 pounds per square foot. Right. So here you could see on the left photo, that's a shotcrete rock work. This is a finished product. And this here, it's a ride that has fog elements, so it has to be lightweight concrete. Upper right, this is carved plaster. It varies roughly about 1.5 inch to 3 inches thick. And it's carved on site, and this is a ceiling. On the bottom right, it's a shotcrete rock work. Also, that's a lightweight concrete, and this is over a water ride. So this just gives you a sense of what rock work would look like. Other theme element would be the show set pieces. Now, these are kind of hard to define, but really it's just anything that is not rock work are considered a show set. Now, material of these elements could vary. So they could be FRP, fiber reinforced plastic, GFRC, glass fiber reinforced concrete, or MDF plywood, or some sort of lightweight wood, such as balsa wood. It could also be lightweight metal pieces and animatronic figures and other electronics, such as LED screen, which I'll show you in a minute. Here you can see how big some of these show set pieces are. This is a chain looking kind of show set piece, and you can see the people right next to it, and it gives you a size of how big this piece is. Next. Here on the left, this is actually an LED screen. It's made from a bunch of smaller screen, like a little, I believe, 4x6 squares or rectangles. And they're on a structure that is kind of odd shape, and that's for the ride purpose. Now, trees are also show sets too. So these are some of the decoration that's required to make the rides. Next, please. Here you can see some more example of the show set. This is actually a mix of carved plaster and show set all together in one. So on the left, you can see the LED pieces. These are shiny blue looking squares. And you can see the spikes. Those are all show set, and the door trim around it, and including that helmet looking at the top of the door. And the carved plasters, of course, on the right. Those are the walls that make it look like bricks. Next, please. Here is another example of show set. What you see, everything in there, the gear, the chains, the door, everything, those are all show sets. And you can see how sometimes they could be very large. Next. Another unusual show set piece you can see on the left is this piece of glass. This is actually a 3-inch thick glass that shipped from Germany. And the right is kind of the finished product where that glass is used.
And back to facility design, we're going to cover our first type of building, which is a black box ride. The
wax moth larvae live in anthills. All right. Let's see if wax.
Somebody needs to be muted. And it's not me. Okay. So we're going to have a black box ride with long span trusses. We're going to look at PEMB, which is a pre-engineered metal building. Oftentimes, this is done by a supplier of PEMB metal buildings, but in the cases that I'm going to show you, we actually designed the large span trusses and the entire building. The exterior is often used in insulated metal panels because they're inexpensive and they go on quickly, and they don't have very much aesthetic appeal, but it's mostly back of house and it's mostly invisible from the guest. And then they typically always have a themed exterior queue or partially exterior and interior queue and cover that the people queue up and come into the building. So here's an example from showing the Q building, which is kind of the conical shaped roof, and coming in to a black box ride, which is behind there, the gray, which doesn't really show very well, but this is kind of a stylized rendering of it. And looking at the structural model that we created for this building, you can see the conical roof here, and then this is the ride building back here that is in the back, which is all long span trusses. The trusses span about 250 feet across the space. The depth of the trusses, as you'll see in a minute, is about 16 feet to 17 feet deep. So here we're looking at the cross section through one of the trusses, and you'll see that the top cord carries compression, the bottom cord carries tension, and the depth of the truss creates a couple that allows that space to, or allows that piece to carry load. My gag went off a little too soon, I'm sorry. But so the other thing that happens often is Walter comes along with large ductwork, and he needs to fit all of that stuff through all of our trusses. And so we spend hours and hours doing clash detection with Walter's ductwork. And then oftentimes the big Walter drops a big piece of equipment on top of our roof. And so we have to carry additional weight and units that are hidden either within the ductwork, or I'm sorry, within the space of the trusses as well. So there's a lot of stuff that hangs from the bottom cord of the truss. Usually there's a catwalk system that will either be integral within the webs of the truss or hang from the bottom of the truss. And then there's going to also be a lot of themed elements that hang from the bottom of the truss or are supported laterally at the bottom of the truss. So these trusses are very heavily stressed. They have to span long distances. So they get pretty well worked. So here's a connection off of the truss. This is actually the bottom cord coming in from the left and tying into the column. And what happened on this design is that the span was so great that we had to create additional stiffness with the column in order to get the truss to function correctly and to get it to resist wind loads. So instead of a normal column, we ended up creating a truss column. And you can see that in this case, we had some very heavy detailing that went into place. The two vertical elements that you see on the left and the right are actually boxed wide flanges. And so we had to create a built-up section in order to handle the stresses that were taking place, as well as the bottom chord of the truss, which comes in from the left, was a boxed wide flange shape that because the stresses were high and we were trying to limit deflections and create a relatively vibration-free truss system. So the next facility I'm going to talk about is a themed ride building. So the black box system, very regular geometries, very regular grid system. Everything follows a very rectilinear pattern. With a themed ride building, we get very unusual geometries, and we get a themed structural system. In other words, the structure actually becomes part of the story in a larger way. The ride integration happens within the facility. We have to build support for the ride, and we have to build accommodations for the ride to pass through the structure. We always end up with some sort of ride connection inspection issues. And so trying to, as a ride goes through its life, there's periodic instances in which all the connections need to be inspected. And that includes those that anchor it to the structure or anchor it to the foundations. And so having those visible is a very important aspect of putting the ride together. We also have heavy theming loads because, like I said, the building is part of the experience, and there's heavy theming to create the appearance of the theme. So this is an example where we have a domed atrium space that is very park-like inside. And there's a roller coaster that goes through a mountain, and it's a mountain of rockwork on the left side of the screen. The back, where you see the flat roof, is a service bay for the coaster and for the coaster ride. The soil at the site was very soft, and that's why we have so many piles under the building, because the high water table and low strength of the soil required a lot of piling. So here's a kind of an interior rendering of what the dome space looks like. We have these big structural steel ribs that go up in an arc to the top of the dome. And we have round pipe elements that form the girts, essentially, for the curtain wall system that's going to be applied to the dome. Here's a rendering of, actually, this may actually be a photograph, I'm not sure, of the mountain. And you can see the roller coaster passing through the mountain. And you can see the entry to the ride on the right side. So all of this mountain had to be structured out of structural steel and then carved rockwork, much similar to what George has been talking about on the rockwork slides. So here's a plan view of the top of the dome. You can see that we have the radial armed structural steel box sections that we used as the ribs to support the dome. And then the circular shapes are all of the bent pipe sections. We chose to use a pipe section for these girts because we initially thought, oh, let's use a box section. But the box section would have to be bent in two different radiuses, in two different axes. And so it became very complicated to specify all of that and actually to build it. And so we elected to use the pipe sections because they can be rolled much easier, as well as they're a little less costly than some of the tube sections. But it did complicate some of the connections. Trying to connect things to a round pipe is a little more difficult than to a flat surface. Also of note is the center of the dome was used to support mechanical equipment and I think a control room as well. So we had some space in the center of the dome that was used for back of house type purposes. So here's a little stress flow or force flow diagram that shows how this dome, which is actually a very stable shape, and when it's shaped properly, the axial compression builds up in the dome as it comes down the rib, and there's not a lot of bending or flexure that happens in these ribs. Most of the stress is due to axial compression. But as it comes down, the dome doesn't completely come to a 90-degree point, and so there is a large thrust, horizontal thrust, that has to be resisted by the foundation, and vertical support as well by the foundation. So we built a ring foundation at the base to help us resist this horizontal thrust, and supported the foundation on piles to pick up that vertical component. Now, some of the stresses got quite high in these tubes, and so we also had to think of how a contractor was going to build it. So each of these sections of the radial arms, we had to come up with a temporary bracing, temporary bolting condition that would allow the pieces to be put together and then secured and then welded after the fact. And the welding was quite heavy, and you can see that. So we had this welding designation is for a full penetration weld, and what it means is that the full thickness of the metal had to be welded. It's not just a surface weld. Some additional connections showing the bolt up and the welding required. So the last type of facility building that I'm going to talk about, and then I'm going to turn it back over to George after that, is a restaurant and retail space. Usually there's a large amount of theming, a lot of open spaces. There's seating areas for eating, but the theming is very high because there's a lot of guest contact. So this is a pier building concept that we worked on, and it's, if you think of like Santa Monica Pier, that sort of thing, having an amusement zone at a pier. And so this is a rendering of the building. This is our structural framing model. What you see at the top, that the undulating steel that goes up and around is supposed to look like a roller coaster. There's not actually a roller coaster on it, but it's themed steel to look like a roller coaster. So this was part of the facility scope, and it was our job to figure out how to structure this so that it looked like a roller coaster, and we could brace it back to the building. The roof structure spans open space below and houses several small amusement attractions and fast food options. So this is a very heavily themed building, and one of the things that's difficult is I alluded to earlier, is trying to get an accurate assessment of what the themed elements are going to weigh and how they're going to attach without having all of the specialty contractor and vendor input up front. So we work through these support designs with some of the vendors who are generally brought on board to help us a bit, as well as some of the folks that work for the theme parks have specialty knowledge, and they give us a lot of assistance in terms of how these pieces are going to be configured and what they're going to look like and what they might weigh. So we put together a diagram on the drawings, and I'll blow it up in a second so you don't have to strain your eyes to try to see what it says, but it tells everybody involved in the project how much we assumed each one of these pieces weighs, because it's very critical to the design of this roof system to make sure that we don't exceed those weights. And if we do exceed those weights, we need to go back and recheck the stresses and the elements that we were working with. So here's a little bit of a blow up, and you can see that we've identified each of the pieces with a part number, what it's called, how much we anticipate the weight to be, and what the attachment detail is, and what we're expecting it to attach to. So we're trying to tell the vendors exactly what we expect from these pieces before they get involved in actually constructing them. So here's a section through that pier building. Like I said, it's on the inside. There's some amusement attractions and little freestanding huts and things that had fast food and other items and retail items. So this was also kind of a organized around an arch. However, it's not a perfect arch, and it also had some truss elements, which were really at the top of the roof. You can see a trussing element that looks like it might do great things, but it kind of stops when it gets to that flat roof. And so it created kind of some unusual stress conditions when we started going through the analysis. And some of the load started to go out and load the columns at the exteriors. But most of the load continued down the arch piece. And so it creates once again, we have a large horizontal thrust force that has to be resisted, and that vertical component just from the weight and the live loads in the roof system. However, the small amount of load that pushed out to the side at the flat roof created some interesting detailing issues. Trying to create an element that could resist that thrust force and not deflect too much, as well as could be anchored into the concrete podium below. And so here's a three-dimensional diagram of all the pieces. And the essence of this is that there was a lot of load that had to go through these particular elements, and a very large anchorage force that had to be anchored back down into the concrete. And with that, I'm going to turn it back over to George, and he's going to talk about rockwork support.
Okay, so now I want to talk about how these rockworks are supported. Generally, there's a primary steel, and these are facility framing. So this could be, the dark ride or whatever, not the outside of the building. Not necessarily steel, but it could also be concrete, which I'll show you a photo in a minute. Then there's secondary steel. These are miscellaneous steel that really extends from the primary steel, the facility framing, to pick up the rockwork loads. And this could be, HSS section, which is a hollow steel sections, right? Or tube steel, or angle irons. And it could also be cold form metal framing. These are light gauge metal framing, almost like a wood, but it has a different shape. Behind the rockwork finished surface is what we call chips. And these are kind of 5x5 or 6x6 wire mesh. You could imagine a rebar kind of gridded with a metal lath over it, and they have special machine that could bend these chips into a different shape to follow the rockwork finish profile. Next. So here you can see example on the left. This is rock work next to an exterior wall, and so it uses the exterior wall as a support, and it has framing on this coming off the exterior wall. I actually have an example photo of this later on. I'll show you. The photo on the right, or the pictures on the right, that shows a Rockwood Tunnel, and you can see the main tube steel that's forming the tunnel. Then you got all these angle irons, smaller tube steel coming out to pick up the finished shell surface. Next. Here's an example of the outrigger of the secondary steel and the main support steel for the rockworks on the left. And you can see that the base building of the main facility building is actually a concrete building. On the right, this is actually what that mesh or the chips looks like. And you can see also, you can see the main outrigger that comes out to pick up those chips, and the outline shows what the chip would look like for each piece. And they usually have three-dimensional models that when they fit into the computer, this machine can generate each chips and bend them accordingly. Next. Here's a view from the backside of the finished rockwork surface. And you can see the support framing, the main support framing, and you can see the chips, the shell on the outside. And you can see there's kind of a grid pattern to that, and you see how it's bended, and you know. Next. Here's that example where we frame the rockwork to the exterior wall. We actually do this out of cold-formed metal framing. On the left, you can see all the cold-formed metal framing coming out in all different ways. The picture on the right is actually taken from a different angle, but that's the same wall. That's the finished product with painted to make it look like a rockwork or make it look like a mountain. Next. Here's another example of the chips. This is more complicated. It's actually the same picture as the left one. It's just more focused on the bottom of this upper on the right picture here. The right picture, you can see the chip for, I kind of highlight that. It's again, it's, you know, bend rebar with metal lath over it to form the backing for the rockwork, shotcrete, or plaster. And this one is really trying to model a fallen tree. So you can see how complicated it's trying to model the roots on the right. And it could get really complicated. Next. So for show set pieces, these are mostly vendor driven, if not all vendor driven. And they could be made out of different materials depending on the vendor's choice. It could be FRP, GFRC, plywood, which I mentioned earlier. The issue with these show set pieces is all the weight and the support off of the main facility building. So the weight is now important for the main facilities, and vendor has a preference on how they want to build these show set pieces. So the vendor will come up with what their final weight would look like, and then we'll go back and forth between the main facility SUR to negotiate, or if it falls within their assumption. If not, then you know the vendor has to redesign again to make sure they can make it lighter or make it into a different material, etc. The next thing that's very important for the show set pieces is guest abuse load. These are, some of these show set pieces could be touched by guests. So therefore, they are subject to all sorts of different abuse coming from the guests. Guests could be hanging on them, could be stepping on them. etc. So usually we design 2 to 2.5 times load required loading for some of these guest fuselage. And again, the main thing is trying to stay within initial support parameter given by the SEOR. But sometimes these are just not possible. So next. Here you can see some of the internal support. On the left, you can see that big chain I showed you earlier. On the right, it's if you've taken that shell away, the FRP shell away, that's what the support for that internal chain would look like. It's just a bunch of welded tube steel, and they would have FRP pieces kind of clad over it. Next. Here is another picture of a gear, of the large gear. And this gear just happened to hang from the ceiling. So on the bottom, you can see all the internal support for that gear element. And the middle is actually the hanger support framing to attach to the gear to the ceiling. And the upper part shows the ceiling framing. And these are actually middle step framing between, looks like the structural steel. Next. Here is another pipe as it shows a piece. The bottom right, you can actually see, I kind of highlight in blue dashed line. That's the main structural steel support for that pipe. It's made out of tube steel. And then the right is just a bunch of plywood form that forms the round shape of the pipe. And they clad that over with FRP. Next.
So to kind of finish off the facility design and the processes that we go through, we have tools for design and coordination that we use. I like to start all of the buildings that I configure with pencil and paper. I like to take, for instance, the long span truss and convert it to just that simple tension compression couple and figure out, okay, how much load is on it, how much tension and compression is going to be created in the top chord, and what size piece of structural steel would I anticipate to be in there. I'll take those preliminary sizes and do some additional calculations, and then we start feeding that into a model to get some sense of how that fits in the space. So we're doing some simple computer models for analysis at this point. And then after that, we start to take a look at putting together our structural drawings, usually in Revit. So we start feeding our Revit operators some of the sizing so that we can start doing clash detection and making sure that it fits within the architect's concept. Once we have a three-dimensional structural model in Revit, we can actually export that now to three-dimensional, pretty sophisticated analytical design software. So in this case, we typically go from Revit to RISA is our usual application. In the buildings that I showed you earlier, we went to SAP 2000 because that was what was available at the time. There's also a lot of clash detection. Once we have a structural model and we have all of our parts and pieces coordinated with the architect, we look at clash detection with the mechanical, electrical, and plumbing, so that we make sure that all of the parts and pieces fit together and nothing's conflicting and trying to occupy the same space, as well as with the ride and themed elements. As I mentioned earlier, the design phases typically we go through a blue sky, a schematic design, a design development, and at each stage we're just further pushing the development of our drawings along, not unlike any other building design. I mean, it's a common this is the standard for design phases in the industry. So schematic design, design development, construction documents, and there's always revisions and changes along the way at each one of these stages based upon whether things are in budget or whether things are meeting their intent in terms of theming, and whether the current concept of what the building wants to be evolves. We also have drawing and calculation production. So doing structural modeling on Revit doesn't create drawings. And so there's a whole process of sheeting and a whole process of detailing that has to happen sort of independent of modeling the pieces. In calculations, once again, we typically are using three-dimensional design software to aid us in that. And we have those original calculations that we did by hand or with simple models. We go back and we look, and we're making sure helps us with a verification process to make sure that we're back checking and things are happening in a way that we thought they would. And if there's discrepancies, we try to go back and figure out why there are discrepancies between the simple models and the more complex models.
So for the theme element, it really all started with the shop drawing process. Shop drawing would show the internal framing and its support condition and any kind of load imposed to the facility steel. The shop drawing also allows the vendor to create what they would like to support for the theme element, what the internal support. Then we take that internal support, then we run it through our analysis software, RESA, SAP 2000, or any other software that we use at the time to validate the support, the load imposed onto the facility. And once the shop drawing is submitted to the SER or any all the stakeholders, then there's a review process, there's a back and forth. As I mentioned earlier, we need to fall within the assumed weight in the beginning of the project. Now, most of the time that may or may not happen, depending what the vendor kind of have a vision of what they want to use. So for example, this vendor would use plywood a lot, then their element would be a lot heavier than what's assumed versus, FRP or GFRC pieces. So then there's a back and forth process about that, and we have to revise the support condition and give it different load criteria back to the facility to make sure they can support it. Next.
So the last thing we're going to talk about is the construction phase. This is a saying that I think a lot of us have always used. The only constant in life is change. There's a Greek philosopher. He's also known as the weeping philosopher because change can sometimes cause a lot of angst, I believe. And so the construction process, the whole design process is about managing change, I think, through to try to get to a set of completed documents. Then when we get to the construction process, it seems like change takes on a whole another dimension a lot of times. So oftentimes during construction administration, we're trying to manage design updates. So as the contractors are building, there's still some design that's taking place. For instance, the vendors are coming on with some of their specialty items. And as George alluded to, sometimes their concept of how they want to build things or what they're going to build things out of are heavier than what we've assumed. And so we're constantly doing design updates to reevaluate those things. Value engineering and cost overruns. Everybody wants to stick to a budget. Oftentimes, once the final numbers are in from all of the subcontractors and the general contractor, there are cost overruns. And so they generally come in with value engineering concepts that the owner evaluates. And those value engineering concepts sometimes require some design changes or some revisions or some modifications. Late vendor input. So once again, the later the vendors come in, oftentimes that can put our design process or put us back into a design process during the construction process. We're managing shop drawings as well. So we're getting shop drawings in, and oftentimes the shop drawings have changes on them that aren't reflected on our facility drawings. So we have to manage that process. Is this really a shop drawing, or is it a change order request, or is it an RFI disguised as a shop drawing? So keeping track of all of that and making sure that the shop drawings actually reflect what are shown on the structural documents is an important process for us. RFI. No matter how good we think our drawings are, no matter how good we think our specifications are, there's always questions. And so there's always, in buildings that are as complicated as these are, there's thousands of RFIs that will be generated during the construction process from beginning to end. And keeping track of those and keeping track of what the responses are, keeping track of whether there's cost impacts, all of those things keep us very busy in the RFI process. We also have to go to the job site and perform structural observation at critical points within the construction process to make sure that our drawings are being interpreted correctly, and that what is being built is represented on the documents. And then just managing all of this with this change, keeping track of the RFIs and keeping track of design updates, all of that sort of stuff, just sort of juggling the whole process all the way through construction is pretty exciting, and it's pretty exhausting, and it takes a lot of effort. And that's all we had for you today. Thank you very much for attending or listening in and watching on YouTube.
Thank you.
Good job, guys. Very good. So we do have several questions. Looking at our time limit, I think we can probably take most of these. Let's see. The first question is, I'm going to direct this one to Mike to start. What has been the toughest problem you have solved that required compromise with various disciplines?
Toughest. Every project has its difficulty. I think that probably I remember this one because it was very early in my career, but we had an animatronic figure that was on a very tall frame, and we were told by the vendor that this animatronic figure weighed 20,000 pounds, and it would generate 10 G's of acceleration and deceleration. And 10 G's at 20,000 pounds is 200,000 pounds, and it was on a very high frame. We actually didn't believe that, and I actually at the time went over to UCI, and I knew a professor there in UCI, is University of California, Irvine. Knew the professor that ran the structural engineering department, and asked him if he could create a model for me of the frame and the moving element, and he did. And so basically he showed that it was impossible you couldn't create enough energy to get this particular piece to go to accelerate at 10 G's nor stop at 10 G's, that it would essentially destroy the piece. And so after much consternation and working with steel vendors and working with the general contractor and all that sort of stuff, we decided that we came up with a way to sort of configure this frame so that it could withstand those level of forces, worked with the foundation contractor, all of that sort of stuff. And then, so we came to a compromise that yes, we can do all of these sorts of things. And then at the end of the day, they measured the forces on the animatronic, and it was nowhere near that. It was under 1 G. So, so it's very overstructured.
Well, thank goodness for that.
Yes.
So the next question I'm going to direct to you, George. In design, where do you draw the line between live and superimposed dead loads for show set design elements?
The way I looked at it, if that shows a piece would move, I would consider that as a live load. And of course, there's a dead load of components to that show set. Any other elements that usually don't move and but stuck onto a wall or a framing or hangs from somewhere, then we kind of consider that as dead, and that will be superimposed dead load.
Cool. Okay. Mike, I think you'll like this next question. When do you decide the specific building materials that will be used? Also, have you had to change to another material after the project had already begun?
Yeah, it's so in most cases, we're looking at structural steel for the larger facilities. In different parts of the country, for instance, in Florida, they use a lot of precast panels because they don't have to worry so much about seismic loads. They're more worried about hurricanes. And so heavy weight, heavy componentry kind of fits their environment. Whereas in California, heavy componentry really doesn't fit our environment very well. And so we tend to try to get a lighter structure, which the structural steel sort of facilitates. But it really just depends on what the use is of the building. Like the one building, the pier building that I showed you, the use of the building was going to be lots of little huts and lots of little sort of kiddie rides, amusement rides, kind of like rides you see at a county fair or something like that, that would need to be attached to the slab. And we couldn't get everything to line up with columns below. So putting in a concrete flat plate in that case was very effective because it allowed all of those things to be loaded at any point. We didn't have to match it with beams. And so we had a nice thick concrete floor slab that allowed that sort of diverse application of elements to be smeared across that floor. Whereas the roofs and those sorts of things, you want to keep those as light as possible. So typically we're into some sort of structural steel solution.
Okay. And the second part of that is, have you ever had to change materials during the project?
I don't remember ever having to change materials in the middle of a project. No, we do sometimes, as George was alluding to, there are different ways to do some of the secondary systems, like the wall systems that enclose the building. And so sometimes you'll switch from like an insulated metal panel to a wall that is framed with metal studs and has rigid insulation attached to the exterior of it with a plaster finish on it. Those are the types of changes that I've had, as well as sometimes some foundation changes when you get on site and you find that no, maybe we need a couple of piles over in this location instead of a spread footing, but not really wholesale material changes after the design is complete.
Okay. George, this one's for you. What are some of the challenges you run into when an existing building is being reimagined for a new use or a new attraction?
So when you're dealing with existing building, depending on how old it is, usually, hopefully they have drawings or they have that show what it is. It's what it's made of, foundation support and stuff, and then how they want to theme it. Luckily, a lot of new rides nowadays is more projection based versus actual like figures and props that made up the story. Projections allows them to do quite a different things, and it's more moving and exciting, I guess. So if they're doing a lot of props, then we got to examine those props, how heavy they are and how they would be attached to the existing building. So those are the challenges that we'll have. again, it's hard if we have drawings or not. Sometimes the building is too old. They don't have anything. Then there's the investigation phase, and we have to go out and look at it. And sometimes you find corrosion, and you have to fix corrosion. There's just on and on problems. More difficult.
I think we're working on some of those projects together right now, as a matter of fact.
Yes, we are.
So Mike, this one's for you. You hinted at this before, but what are some of the challenges when adopting a non-seismic design, for example, in Florida, to a heavy seismic design, for example, in California, when the expectation is to keep the architecture nearly identical? Are you given the ability to push back on the architecture and the design?
So yes, to a certain degree. So the best example is the lift of E.T.'s Adventure, which is now in California. It's Mummy. I think it's the Mummy coaster. But in Florida, when we did that lift, it was taken from a precast concrete exterior, and we don't use tall precast panels like that in California. And so we switched the exterior wall system to structural steel columns with girts on the outside to support metal stud framing. And that metal stud framing was plastered. So the weight went down tremendously. And it also allowed us to introduce a brace frame around the perimeter with that structural steel. So we were able to comply with California seismic requirements and not really get into the inner portion of in the theming of the ride itself.
Got it. Cool. George, one more for you. With the world wanting to move away from concrete and its effects on the environment, what do you believe will be the next building material to support themed entertainment, building, and construction?
Structural steel seems to be a very popular choice, but I see that maybe some more light-gauge steel becoming more prominent as the, but again, the light-gauge steel kind of now is just all limited to a secondary, either wall framing or interior wall supports. So yeah,
there are lower carbon concretes that are coming out as well.
Yeah.
And so people are aware of the the amount of energy it takes to produce concrete and the amount of carbon that it produces. And so there's lower carbon alternatives. Trying to find a lower carbon alternative concrete that works for your performance specifications is always a little bit of a challenge, trying to use new materials and figure out how to, what their long-term durability is, what their shrinkage characteristics are relative to normal hard rock concrete. And, so those are all the challenges. I think we're seeing a lot more of that in the construction industry in terms of trying to get to a lower carbon solution for most of those types of materials.
Okay. And then we'll wrap it up with this last question for you, Mike. You mentioned animatronics being a major source of loading. How do you deal with their movements? Do you have any say in how they're anchored and installed, or is that completely up to the engineers in charge of their design?
Usually the where they're anchored is not our choice. How they're anchored, we have a lot of say in how they're anchored. And how they're supported within the facility. So generally we're trying to keep all of the stresses, because we're looking at literally millions of cycles on these things. And so any weld stress has to be taken down to very low stresses, under 5,000 PSI. Usually we design welds for 30,000 PSI, that sort of thing. So we take the stresses down very low on those connections, as well as on the bolted connections. We take those stresses very low so that they can have repeated cycles without fatigue. And that's really the essence of doing connection design for anything that has repeated motion like that and a number of cycles over its life. You got to be very careful with how high the stress levels get in those connections.
Got it. Okay, well, we put you under the spotlight here for about an hour. So I think I want to say thank you on behalf of everyone watching. You guys did a great job, and we appreciate you taking the time out of your busy schedules to tell us more about it. And with that, I think we're going to wrap it up. Our next session should be in the next couple of months, probably in June. And I hope to see a lot of you there for that session as well. So thank you again, gentlemen, and we'll talk to you guys soon. Have a great
Thank you.
day.
Thanks, Walter.